Okay, so some more radio waves. We talk about propagation now. Talk about sunspots and refraction and all kinds of good things. Uh, the atmosphere can affect radio waves depending on their frequency and time of day. Uh, our atmosphere is around the Earth is divided up into several sort of shells. We call the ionosphere uh, because it contains ionized particles. So radiation from the sun has enough energy to create free electrons in the oxygen and nitrogen and other gases that are in the atmosphere, and create positive and negative ions. And those ions can affect radio waves and cause them to bend or refract. So when we talk about, and it's frequency dependent. So UHF and microwave signals typically aren't refracted, at least not very much. And they're normally line of sight type signals. So they will go straight through the atmosphere. In the VHF and UHF range, the lower UHF, there is some slight bending. So you can get some actual curvature. So instead of being straight line of sight, where if you've got a handy talkie at 2 meters, normally that signal wouldn't go any farther than the visual horizon. So depending on how high you are, determines how far away the visual horizon is. And the formula to calculate it is it's 1.23 times the square root of the height in feet. So if you're holding your handy talkie 5 feet off the ground, assuming you're like 6 feet tall, then the distance to the visual horizon is going to be 1.23 times the square root of 5. Whatever that comes out, it's a few miles. So if there's another person on the same frequency that's also 6 feet tall on the other side of the horizon, a couple miles there, you could do point to point between those two people at twice whatever that visual horizon distance is. Now, it turns out that you can actually get some bending of the wave. So you get an over the horizon effect, which is called the radio horizon. And that is 1.414 times the square root of the height. So you see it's about 18–19% farther. So that particularly on the 2 meter band would let you get maybe an extra mile or two between 2 points without having to go through a repeater, which we'll get to later. Here's just a graphic representation of the visual horizon and how you use the formula. So you would calculate distance 1 and distance 2 and add them together. Now, if obviously the higher the antenna is, the farther that visual horizon is going to be. So if you're up on top of a building or on top of a mountain, you're going to go a whole lot farther because it's line of sight. It's how far you can see assuming there's no obstructions. So why is the radio horizon for VHF and UHF signals more distant than the visual horizon? You got a guess out there?
Charlie, atmosphere refracts radio waves.
Right. Slightly. Why are simplex UHF signals rarely heard beyond the radio horizon? And by simplex, they mean basically point to point. You're not going through a repeater.
Charlie?
Well, let's see. That's right. Usually I was going to point out, there's usually two answers that are really out in left field. I guess there's kind of two. A is really not a very good answer, and B is really absurd. The FCC can't prohibit signals going anywhere.
Plus alpha.
That's a law, but it wouldn't do any good.
Also, weak was spelled wrong.
Which was?
Oh. An alpha to weak. That's spelled wrong.
How about that? Yeah. I can't fix it in this mode. All right. We talked about it being line of sight. Now, there's another thing called multipath, because even though they're line of sight, these signals can reflect off of buildings and things like that. So you can wind up having multiple paths, which is why they call it multipath. And because the signals can being reflected or bounced off of objects, maybe more than one, can take a longer path than another one. So it can actually arrive out of phase or partly phase shifted and cancel out part of the signal. Or just the opposite, it could wind up being in phase and increase the signal. And just by moving a few feet, you could really change that phenomenon and go from a case where the signal's being canceled to where the signal's being enhanced, and move a few more feet and have just the opposite. So moving around can vary the signal strength quite a bit if you have multipath going on. When you're moving in a car, like you've got a mobile installation or you got your handy talkie, up by the window, if you've got multipath going on, you can get what they call picket fencing. Well, you hear it cancel and enhance and cancel and enhance as you move, and the signal will kind of sound like the kid on the bicycle dragging a stick along the picket fence and going blip 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 blip. You sort of get that effect in the mobile operation. If you're doing digital modes like digital voice or one of the other digital modes, which wouldn't expect you to be doing while you were driving, multipath can cause errors because you really need a constant signal for a digital mode. And digital modes tend to be, you either get the signal and decode it or you don't. You don't get a weak signal with static. It's either on or off. This is just a picture showing different types of multipath, and you can see all the possible reflections there. So why do VHF signal strengths vary, sometimes vary greatly, when the antenna is moved only a few feet?
Charlie.
All right. We had a good example of that a few weeks ago. Our club was doing a simplex exercise where we try to communicate with one another on handy talkies without any power, assuming it was kind of a emergency management type of thing. So you assume that the internet and power and everything is down. And it was before the class started, and Dan and I were here out in the parking lot. And I was close to the building, had a external antenna hooked up to my handy talkie, and Dan was out on the next to the street, probably 20 feet away. And in some cases, I could hear him talking to somebody on the same frequency, yet I was getting just static 20 feet away. And then I moved a few feet and things changed. What is the meaning of the term picket fencing?
Type Charlie.
Did you mean Charlie?
Yes, I did.
Well, I hate to tell you, that's not right. It's the rapid fluttering of signals due to multipath as you're moving.
So if you're driving in your car and the multipath keeps changing and it's gonna be at one point canceling the signal and at another point it's gonna be enhancing the signal. So you get that back and forth sound like you're talking into a fan or something like that.
You understand that one?
Um, at the moment, no. Sorry.
Well, let's see. How can I explain it better? I mean, you understand the analogy about, riding along your bicycle with a stick, hitting it along the picket fence.
Yes, I understand that.
Okay. Well, it's the same kind of effect when you're in a car, whether you've got a mobile installation and external antenna on the car, or you've got a handy talkie, because of multipath, which means your signal's being reflected off of objects, buildings, and things as you go by. Sometimes you get two signals that arrive where one has taken a longer path, so it's what we call out of phase. In other words, if you were to compare the two sine waves, in one signal, the peak of the sine wave is going to be at the trough of the other signal sine wave, so they'll cancel out.
Oh, I see. Yes. So the sine
Maybe a
waves,
little bit
in a
later,
sense.
they're back in phase and the two peaks are together. So they'll actually double, may double the signal.
So this is talking about more of the sine waves, correct? Just the way
Right.
the way they look, it'll make it look like a picket fence. Okay.
So what effect does multipath propagation have on data transmissions? That's meaning digital transmission.
I'll guess alpha.
No, it would be delta.
Okay.
The error rate is going to increase because you're going to lose some signals. And depending on the digital mode, if it doesn't have any kind of error correction where it may resend the signal, you're going to have dropouts. And we call that the error rate, how many packets are received, or in the case of some of them, the bit error rate. You may not be receiving all of the bits because of that. So digital modes are very sensitive to these kind of effects, and you need a consistent signal for a good digital mode. Okay, talk a little bit about repeaters. We've talked about basically simplex mode where we're going point to point, because that's very limiting to normally a few miles. We have what we call repeaters, which are a receiver transmitter pair that normally get installed up on top of towers or high buildings so that their direct line of sight is much farther. So you can take your handy-talkie and access a repeater, which then takes your signal and this is what we call repeats it, actually on a different frequency, an offset. So somebody else that's within line of sight of the repeater can pick up that signal. So you can communicate over much larger distances using a repeater. In the case of our NASA repeater that's on top of the VAB, it's 525 feet up, and it has a radius of over 30 miles. So it means you could be talking to somebody 60 miles away through that repeater if you're both within line of sight of it. In some cases, you may not be in line of sight. There may be an obstruction. It's possible that you can reflect a signal off of a building or something to actually get to the repeater where you can't, where it's not in direct line of sight. You could have an indirect line of sight by a reflection off of a building. Kind of like what was happening with multipath. And in this case, it's a good thing where if you can, find the path, Another possible thing is called knife edge diffraction, where it's just like light, because radio waves are just lower frequency light waves. Light or radio waves will bend or refract around a sharp edge. So they will actually bend around the edge of a building or the top of a building, or supposedly over the top of a mountain peak. I wouldn't think it's sharp enough, but apparently the books say it works. I don't know firsthand. So those are different ways to get to a repeater when you don't have direct line of sight. Another factor is absorption. When we're talking about VHF, UHF, microwave, and mostly UHF and microwave, signals are absorbed by water. So heavy vegetation, trees, things like that, since they're have a lot of water in them, will absorb those signals. So will fog and rain.
That's another reason why ranger towers are built so high, right?
Well, that, and so they can see smoke. And actually people will absorb it too, because we're mostly water. So if you got a room full of people, your signal, like your cell phone and stuff, gets absorbed more than an empty room. It doesn't have any real effect at the lower HF frequencies, down below like 30 megahertz. This is showing where we got a repeater up on top of a tall mountain or something. So we got two people that obviously can't see one another line of sight because of the mountain, but by going through the repeater, okay, they can get there. And in a case like that, I mean, you could have, I don't know, think how high it is, 100 miles apart, maybe. When using a directional antenna, how might your station be able to communicate with a distant repeater if buildings or obstructions are blocking the direct line of sight? Now, you wouldn't necessarily have to have a directional antenna, but it would work better because you'd have
Bravo.
your signal in one direction.
Bravo.
That sounds good to me. And we talked about knife edge. Here's kind of a picture showing how it would diffract over a mountaintop. Most mountains don't look that sharp. Anyway, they claim it works. There's a question on the exam. So. Which of the following effects may allow radio waves to travel beyond obstructions between the transmitting and receiving stations?
Alpha.
Alpha.
Alpha. Yeah, Faraday rotation has nothing to do with it. I don't know what quantum tunneling is. It's well beyond amateur radio licenses. And Doppler shift is something we'll talk about, but not yet. What is the effect of vegetation on VHF and microwave signals?
Bravo. Absorption.
Right. Okay, polarization. I mentioned it earlier, where because of the wave being composed of an electric field and a magnetic field, we normally just care about the electric field. And most of our antennas are designed to work with the electric field. There are newer magnetic loops that would actually receive the magnetic field portion of the wave. But for now, we're going to talk about electric field. And we define the polarization of the signal as the orientation of the electric field with respect to Earth or ground. So if you have a vertical radiator, like a vertical antenna, you're going to have vertical polarization because the wave is moving back and forth along that vertical antenna element in a vertical orientation relative to the Earth. If you've got a horizontal radiator, like a half-wave dipole wire antenna, it's going to be moving back and forth across that dipole, like shown in the animation, in a horizontal direction. We call that horizontal polarization. So when we're doing VHF and UHF, line of sight type things, if we have differing polarization, you get a reduced signal. So normally, in the case of most VHF, UHF, you're going to have a vertical antenna, like if you've got a handy talkie with this little rubber ducky, or if you put a longer antenna on it, it's a vertical antenna. And you need to hold it vertically if the person that you're trying to talk to is holding his or her handy talkie vertically. If you rotate them 90 degrees or cross polarize them, you're going to get a very reduced signal. It has to do with the aperture of the antenna and stuff we won't go into, but I think there's a next slide which kind of shows the effect, and it works the same way with visible light with a polarizing filter. In the case of trying to do VHF and some UHF for long distances, where you're actually taking advantage of some refraction, you typically are going to be using horizontal polarization just because it's easier to do horizontal antennas than vertical antennas. Most VHF, UHF repeaters are going to be vertically polarized and have a vertical antenna. For one of the main reasons is it gives you an omnidirectional radiation pattern. And that's really what you want for that repeater, so it can receive and transmit in all directions. This is just showing the normal linear polarization. And then down here is what happens when we get what we call circular polarization, where the phase is changing. So the polarization is actually rotating because of that change in phase. If we took if you're familiar with a polarizing filter, if you're not, if you've got polarized sunglasses, that's a polarizing filter on them. So if you've got non-polarized light over here, and you run it through that filter, in this case, you're going to have vertically polarized light coming out. Now, if I run that vertically polarized light through another polarizing filter that's rotated 45 degrees, what I get out of it, okay, is that same amount of light times the cosine squared of 45. If I rotate it again, so now I'm 90 degrees, you can see that what I get out is very much smaller than what I had going in. That's the same effect as if you rotate your antenna 90 degrees. What property of a radio wave defines its polarization? Any guesses?
Charlie, it's a combination of both electric and magnetic.
Well, the radio wave is made up of both electric and magnetic fields, but this wants to know how we define its polarization.
Okay, then beta, magnetic field.
Well, I'll give you one more guess.
Alpha.
Alpha. It's the orientation of the electric field, and we normally say with respect to the Earth. It's got to be relative to something. So we only care about, when we talk polarization, we only care about the electric field part of the wave. What happens when antennas at opposite ends of a VHF or UHF line of sight radio link are not using the same polarization?
Bravo.
Bravo. Signal strength is going to be, I'd say, greatly reduced. What antenna polarization is normally used for long distance CW and single sideband contacts on the VHF and UHF bands? So basically for long distance communications, trying to do propagation on VHF and UHF. Because it's different than what you would do for regular simplex or repeater operations.
Charlie?
Charlie. It doesn't have to be, but typically it's going to be horizontal. Because it actually turns out, and I'm going to get ahead a little bit, when radio waves are refracted off the ionosphere, there's an effect which causes them to be refracted as an elliptically polarized waveform instead of a linear. So if it was vertical or horizontal polarized, going up and refracting off the ionosphere, it's refracted back as an elliptically polarized waveform. So you could receive it with either horizontal or vertical polarization. Okay, so we learned about line of sight, what the formula was for the visual horizon, what it was for the radio horizon, and due to slight refraction, it goes a little farther than you could actually see. We talked about multipath, where the signals can arrive in phase or out of phase, so they'll either add or subtract. If you're moving, that effect causes what we call picket fencing, where you hear it rapidly being in phase and out of phase. The multipath can cause high error rates on digital or data transmissions. You can use reflections off of buildings to reflect a signal to get to a repeater or even to another person, simplex, possibly. Knife edge diffraction, where waves bend around sharp edges, can be used, where there's obstructions and you can't see line of sight. Water, rain, trees, people, anything with a lot of water, moisture in it will absorb UHF and microwave signals. Polarization is defined as the orientation of the electric field relative to Earth. We use horizontal polarization normally if we're trying to do a long distance on VHF or UHF, and typically vertical if it's a standard line of sight or talking to a repeater.